Thank you so much. Thanks a lot for the warm introduction. I'll share my slides, and in the meantime, um, you know, um, Nihat here kind of was he was a little too humble in telling our story. So I'll kind of set it straight a little bit. I started undergraduate in Istanbul Technical University. I frankly had no idea what I was doing. I didn't even know about MIT. I just kind of stepped into the school. And I just accidentally did really great in mathematics. And I heard this program that, people who are top of class and in a bunch of classes in the first year will be taken to MIT for 1 week. And so I just kind of accidentally uh, met Nihat Hoca that way. And he took me to MIT in my second year. It changed my life. And that was, I think that if I could point to one thing in my professional career that made me come over here is the 1 week I spent with Nihat Berker over at MIT. So I'm really grateful for that.
Sertaç, I'm going to start crying.
It's true story. It's really true story. Had I not made that trip, I don't think I'd be here today. So let me come in and sort of tell you a little bit some of the things for research I was doing. And I will, as Nihat Hoca just mentioned, I also picked up the leadership here for a major laboratory at MIT. So, nowadays I tell people that I'm going to give them a research talk and just insert some information about lids, in a very covert way. But I'll do that, and I hope you don't mind. So I'll start my talk a little bit, kind of telling you about information and decision systems, and in the process, I'll talk to you about lids. It is a multi-professor major research laboratory at MIT. If you're curious about it, go to lids.mit.edu, and then you'll learn more about it there. Lids actually is the longest continuously operating laboratory at MIT. To put it mildly, it is the oldest lab at MIT. It traces its foundations all the way back to 1940, during the years of the Second World War. And essentially what the lab has been doing is it's been applying computing to solve problems of automation. That's what it has been doing in 1940. That's roughly speaking what it does today. In 1940, you didn't have the kind of digital computers or, the thing that I'm using right now to talk to you all the way around the world. You didn't have those. What you had was another professor at MIT invented analog computers. His name was Vannevar Bush. And Gordon Brown, the founder of LIDS, is actually a student of Vannevar Bush, who started the laboratory to work on a number of different projects applying these kinds of analog computers to problems in automation. After the World War II years, one of the things that they did, for example, was numerical control of milling machines. So now this is something that is very, we do this all the time. We went way beyond this, like we have now 3D printers and things like that. But back sort of 80 years ago, this wasn't the case. Milling machines had to be manned by people. And it was really an art to get out some of the most intricate pieces. And so they connected that to a computer, an analog computer, and then a digital computer after that, in order so that they can get out pieces that are very intricate. And that really helped industry grow tremendously so that you could get more complicated automotive parts or aircraft parts. Especially it helped establish the aircraft industry. One of the big projects at the laboratory was called Whirlwind. This was a project to build MIT's first digital computer. The project actually just started by, let's build a real-time simulator that can simulate an aircraft so that we can train pilots. Could actually, in fact, civilian. So how can we, train civilian pilots? But back in 1950s, they had digital computers, but digital computers were too slow. And they had analog computers like these big machines. They were fast enough to compute, but they weren't very accurate. And so in the process, they built an entirely new digital computer in the laboratory. It was the first and the only big digital computer at MIT. And during this time, in order to make the digital computers compute very fast, they invented something called magnetic core memory. That was patented at MIT, and it was an essential component of any computer up until 1970s when the chips first came up. And so that was a major invention in the laboratory. In fact, a company called the Digital Equipment Corporation, DEC, which was a very influential company in the area of computing in the initial years of computing here in Boston, is a spin out from the laboratory. Even MIT's Lincoln Laboratory, which is a huge laboratory, is a part of MIT. It has almost like $1 billion budget, is essentially a spin out from LITS. And then, going forward, the laboratory actually had taken multiple names. It took its name of Laboratory for Information and Decision Systems back in 1978. Even though that is more than 40 years ago, the name Information Decision Systems is so interesting and influential today. And during that time and up until now, the laboratory has worked a lot on control systems, optimization, game theory, signal processing, filtering, estimation, and a number of other topics that has been very influential in the development of technologies like telecommunications and a number of others. And now the laboratory works on a number of other things that are related, but just kind of looks out into the new 21st century. Before I tell you that, I'd like to tell you a little bit some of the organizational details of the laboratory that happened just very recently, right after I took over as the director. The laboratory is now a part of MIT's what's called Schwarzman College of Computing. This is a very big development at MIT that's very recent. In 2020, we've started what we now call the Schwarzman College of Computing. MIT is 5 schools. It's been composed of 5 schools over the past half a century. These are the School of Engineering, that's probably well known to many of you. We also have Sloan School of Management. We have a humanities school, a School of Sciences, where Professor Nihat Berker has been a part of for many years. And we also have the School of Urban Planning and Architecture. And so now we're adding almost a 6th school for the first time in half a century. We don't want to call it a school because it's not in its own silo like the other schools, but it actually cross-cuts all these other schools. We think that the notion of computing can be applied to not only all the engineering disciplines, not just science, but we think, you can apply computing to humanities, certainly to things like economics, but maybe even anthropology. We realize that a lot of these fields are using computing not just as a tool, but computing is a little bit becoming the fabric that constitutes almost some of these fields. And so now we decided to call it a college, not a school, but a college for this purpose, that it cross-cuts everything that we know at MIT. It's a major development. Our biggest donor is Steven Schwarzman of Blackstone. We've also had a number of other donors, many of them MIT alumni who we're very grateful for, who've enabled the formation of this college. So now we have a number of academic units where academic programs like graduate, undergraduate programs, as well as faculty hiring and promotion go through. And also we have a number of research units and research initiatives that are a part of the college. The 2 major research laboratories that maintain space are the Computer Science and Artificial Intelligence Laboratory and the Laboratory for Information and Decision Systems within the college. The college will add 50 new faculty slots to MIT. So for people who may know, MIT has 1,000 faculty slots. So we're adding 50 more to that. And those faculty members will be a part of the college in some shape or form. And many of them will come and trickle into the Laboratory for Information and Decision Systems, which is driving growth for our laboratory. To tell you what the laboratory does today is that we're essentially everywhere that turns data into information and information into decisions. We now know that there's a lot of data in the world. This has been created over the last 2 decades by essentially us putting sensors everywhere, including in your pockets. And now the laboratory develops a lot of inference algorithms that turn this data into useful information and decision-making algorithms that turn information into decisions. The laboratory especially focuses on when this whole notion intersects physical systems and social systems. By physical, I don't just mean sort of physics in the sense of Department of Physics, but it could even be like biological systems, like human health, for example, as well as social systems. And I'll give you some examples. In some cases, you make information available to these physical and social systems and they reconfigure themselves. For example, you can imagine the entire financial system as a social system. Ultimately, yes, there are some computers, but there's a lot of people sitting behind these computers and making key decisions. And sometimes they just see some information out there in the world and the whole system reconfigures itself. And sometimes you deliberately do that through decisions. And sometimes you even use those decisions to update your algorithm so that you can serve these systems better. And, a little bit of a joke is that that's where the LIDS logo is inspired from. Let me tell you a few examples of how we can kind of put inference and decision-making into areas where physical and social systems are omnipresent. One of the areas that we're really interested in is transportation. So imagine you have algorithms for fully autonomous vehicles. I've personally worked on that quite a bit. Imagine fully autonomous shuttles that you get into. They can take you from point A to point B and say in Istanbul, and for much less cost and much more comfort than what's available today. So now that's not where it actually ends. Imagine now they operate in streets where human drivers are also present. Now imagine the kind of algorithms that they need to employ so that they can interact with the human-driven vehicles very well. Imagine if the human-driven vehicles themselves have some form of autonomy. It's not fully autonomous, but how do you make it so that human-driven vehicles are safe, so that they can operate in a way that they avoid collisions, for example, on their own, or they can warn in some nice way the human operators behind the steering wheel. So now imagine the coordination algorithms that would coordinate human-driven vehicles through incentives, like in a game theoretic fashion, as well as the autonomous-driven vehicles in a way that are fully autonomous. So now this would be coordinating the entire traffic. So imagine the kind of algorithms that need to be developed, but you can go one step further. Ultimately, as a society, we're in some form of a social network. So imagine now automated bots that would go on places like Twitter, for example. They would initiate certain kind of polls and collect some opinion, maybe even drive opinion in a certain way. Obviously, you want it to be very open and transparent, but drive opinion in a certain way so that we see some form of convergence of how traffic should be run. And so that they do that in a way that is human-centered and helps humans the best. So this is an example of where you see the physical systems, autonomous, semi-autonomous, humans in the loop. Some of the humans may not even know that there's autonomous systems in there. And these autonomous systems have quite a bit of a reach. They go on, reach out to social networks to organize everything. So this is a good example of where LIDS gets in and applies AI and decision-making in a place where there's a real world in the loop. This doesn't end in transportation. You can imagine manufacturing, space, and a number of other areas that we're embedded in. Today, the key research areas include machine learning, data science, and statistical inference. This is a place where LIDS is a powerhouse. Actually, we kind of share machine learning as a field together with CSAIL. We'll be organizing a number of workshops together in a way that is sort of half and half split. But we mainly focus on the data science and statistical inference aspects of it, as well as things like reinforcement learning, for example. We're very excited about autonomous systems and automated decision-making. It's an area that I am invested in quite a bit as well. And we have a lot of people who work on networks and network systems as well. We do a lot of foundational research in topics like optimization, game theory, probability theory, and so on. But I'm very happy to see that more and more recently, we're seeing that a lot of people are looking at demonstrating the impact of our foundational research and applications. This is either demonstrated in laboratory experiments, I can show you some today, but also in a number of spin-off companies. So I've gotten a chance to involve in one of the spin-off companies out of LIDS called Optimus Ride that was just mentioned a second ago. It actually got acquired by Magna, which is the leading automotive supplier in North America. But there's many others who are in different sets of fields, from aerospace to like predictive analytics for retail to things like automated vehicles and automotive. LIDS, as I said earlier, is a rapidly growing sort of community of people. The slide is already kind of old, but we're a little over 200 researchers right now, and we have a number of supporting staff to support our laboratory. Our students mainly come from the EECS department, but that's about half of our students. We also have students who come from places like Aero-Astro, operations research, data science, mechanical engineering, biology, and you name it, in many, many other places. This is all the professors at LIDS. I just wanted to flash their picture, and as I said earlier, it's already old and doesn't include one of our PIs. We're right now 37 PIs and growing rapidly. So that was a little bit about lids. Now I'm going to go to the talk that I actually promised. I'm going to split this talk into two pieces. On the one piece, I'm going to talk about what I call autonomous super vehicles. These are vehicles that are extremely fast, extremely agile. They can make decisions very quickly. If you're curious about this, go to my website, iro.mit.edu, and I'll have in the second part of this talk vehicles that are very miniature. And for that, there's a separate website that I'll show you that. So I'd like to kind of get started on this autonomous super vehicles session of the talk on a bit of a bitter note. I don't know if you're aware. I guess when you're in Turkey, you are, but a lot of lives are claimed in traffic accidents across the world. Just in the United States, where there's a lot of data available, we lose about 40,000 lives every year to traffic accidents. There's 100 people every single day. That you don't get a chance to hear in the United States all that much, but it's a lot of people every single day. Across the world, the number of deaths on traffic accidents is about 1 million people every year. That's a lot of people. In fact, before I could finish the sentence, somebody died, someone on Earth, on a traffic accident. Most likely, that was a young person who actually had more than 50 years ahead of them, and they just died in a traffic accident. Most of these traffic accidents happen at very high speeds. And when we look at the US data, we kind of see some sort of a trend that's kind of going down that actually is enabled by the introduction of an adoption of the seat belt in around 1970s. The accidents per mile traveled has gone down quite a bit, but the miles driven per person has been increasing since that time. So, there's a bit of a balance of power here. But it's pretty clear that, we're a little bit stuck. So when traffic accidents happen at like more than 100 kilometers per hour, it's very difficult to save people, seatbelt or not. And so one question is, how could we actually save people out of traffic accidents traveling at those very high speeds? So now I'm going to show a video. Hopefully it is going to stream well. What you're seeing is a person driving a car and just barely gets out of an accident. So, I kind of pulled this out of Junkin video. And what seems to be a person who's probably rented a Ferrari and just kind of driving it around. This is a lucky human driver. But to be very frank, there's expert human drivers, like people who actually drive these races that if you were to put them right at the time of an accident and say, there's going to be an accident, you have to avoid it in the next 5 seconds, they probably can avoid about 90% of the accidents. Most of the time, what happens is that people just cannot comprehend what's happening. They don't understand and they just cannot react and they crash. A lot of other times they want to react like this person, but they just lack the motor skills. So they want to go to the next lane, but they oversteer and they go and crash into a tree. And because they're so fast, it becomes a fatal accident. Now, imagine systems that can see the environment so fast. Like your eyes, for example, capture images about 100 frames a second. What if you could have things that can capture images at 1,000 frames a second? They can use supercomputers on board. They can even shut down your infotainment system right at the time of an accident to use the computing power available there so that they can see the environment. They can just nudge the car just a little bit, or basically if you're trying to go to the next lane, they make that happen as opposed to you going outside the road. They will probably cut down more than 90% of the accidents. It will be as successful as the seatbelt. It will be the autonomous seatbelt almost, the kind of the little guardian angel, behind the steering wheel that would protect you and they would take you out of accidents. We can't do that today just because we don't quite have the autonomy technology that can enable it. And we don't have the algorithms verified in a way that we can put it into the vehicle. So that's something that we're very excited about. This question of, can we build autonomous vehicles that can operate as good as, or maybe even better than the best humans? And I'm going to call them autonomous super vehicles. It's as if autonomous vehicles that have like superpowers. So now cars aren't the only domain. Humans are also very good at, driving around drones, for example. So here's a fun experiment. This is human pilot. It's a small drone, like a consumer drone that you can buy around. They put a camera on top. And the camera images beam back to a set of goggles worn by a human, and the human is remotely piloting it. And it's just kind of incredible how they can fit through like little openings and go around. It's just crazy to see this. It is impossible to do these things right now autonomously. So it'd be great to develop technology that, we can do similar things in some way. And of course, if you can do this, like people can do the same thing in, for example, forests. So you can imagine things like, search and rescue missions, like, people imagine somebody got lost here, or like they fell and they have a lot of blood loss. Like, can you actually reach them, take them medical supplies in no time? There's a lot of applications that, you could think about. So about a few years ago, I've realized it's actually very difficult to do these things. And humans can do very well. They have all these drone racing events. So I kind of worked a little bit with a few other colleagues on a public challenge. It was called Autopilot. It was organized by Lockheed Martin, who's one of my long-term sponsors, together with NVIDIA, who's also one of my long-term sponsors. We work with a media company out here in the United States. It's called Drone Racing League. And we announced this challenge. The challenge was we invite people to program fully autonomous physical drones and have them race in a real environment. And we're going to make a simple environment and see if people can actually build the algorithms to go around autonomously. And that was the idea. And we offered $1 million prize. And so the sponsors paid for that. It's $1 million US. It's a lot of money. But I was still expecting that we would get maybe 20 teams and we would probably interview them and see who is best and maybe take 10 of them and it would be a great race. We had 500 teams apply. That was more than 1,000 people. And so we somehow had to scramble in some way to find a way to go from 500 teams down to 10. And my team here at MIT, my research team, really stepped up and they quickly pulled together a simulation environment. The simulation environment looks like a bit of a rundown warehouse like this. We have a bunch of gates. And so you need to start in the starting location, go through all these gates, turn around in a figure 8 pattern and finish the entire course. We have some visual aids here and there, but it's very close to real. The drone's dynamics are simulated. You also get sort of the simulation of inertial measurements like you would get on a real autonomous drone. You get a simulated camera that's rendered, very realistically. And you get a few visual aids around the gates to see where the gates are so that you can kind of go through it autonomously. The only difference is that we told people that it's going to happen in the same area, but we're going to just move the gates a little bit slightly, but we're not going to tell people what exactly the locations will be. And we told people to just basically submit the code, and then, we kind of checked them. We used another company who would check people's code, and we ran everything on the Amazon AWS cloud. And so, we would just run their code on the cloud to see what they do against our simulation system. And we put the simulation system completely open source. People can go and tinker it, see what's in it, and build towards it. We had about 80 teams out of 500 submit code that actually was in decent shape and was kind of working. Out of that 80, 40 was actually flying fine. Out of that 40, 20 was flying pretty good. And so, we put together, so they had 3 months to do this. I'm going to pull together, they race one by one, but I'm going to pull together all the trajectories of all the drones. It's going to stream well, hopefully. It's a short video. You can see the drones are traveling fine. Most of them are actually reaching, the top speeds that, we asked them to reach, like perfectly fine and going through it. Yes, there's a lot of, crashes, but even the crashes themselves, they seem to be able to just make it through the gate, for example, here, and then they crash into the gate. So, or sometimes they just kind of lose where they are and then they just kind of go around. But in general, pretty good results. This was actually an interesting experience for us. I'm not going to show you more of the details, but we down selected 11 teams. It was very difficult to pick the top 10. So we picked 11 teams. They actually went to the real race. University of Delft in Netherlands was the winner. And we actually did award them $1 million that they took home. If you're curious, you can go to flightgoggles.mit.edu. It was kind of right here on the side of the slide. And you can kind of take a look at the simulation environment and the race and everything. But what I've realized is that in a simulation environment, which is reasonably realistic, and I'll show you, we can make this a lot more realistic, people actually do really great. but we've realized that, somehow transferring that to reality has been very, very difficult. So, we started engineering all these different environments where we have like a little drone that flies in this empty room. We use motion capture to take its position and orientation and render a completely different environment that, the drone can kind of see and navigate. So I'll show that again. The drone flies in this empty room, but it thinks it's flying here. And so we have all the machinery to kind of generate this imagery and beam it back to the drone. It's as if the drone is in virtual reality, as if it's put virtual reality goggles. And we can also have a human in a different room who can actually put virtual reality goggles. The drone is in a separate room, but they're in the same virtual space so that they can actually like sort of coordinate. This is an interesting kind of a simulation environment where you have the real drone, it's real dynamics, real inertial measurements, but simulated imagery. In fact, the imagery itself is the only simulated thing here. So it's a little bit closer to reality than just kind of running everything in simulation. We can make it even more realistic if we could make this imagery extremely realistic. So for that purpose, what we started doing is we actually started scanning real environments. I didn't tell you, but that whole warehouse was created not by sort of like 3D artists, building columns and things like that, but more like we went to an actual warehouse and we took a whole bunch of pictures and then we recreated the thing that we took pictures of in 3D. This is critical because everything that you're looking at here is actually a transformed image of a real world picture. And so you're looking at the real world object. We're using computer graphics only to take these pictures and synthesize a new view. And over the past few years, we really tried to push this as far as we can take it. So here is the Frank Gehry designed building where LIDS actually sits in. It's home to LIDS and CCEL, MIT's College of Computing is kind of mostly here. And so these are some photographs of the environment. We went out and scanned the first floor and the basement floor of this very building. We essentially created a digital replica. The digital replica itself is very, very detailed. So I'll show you some renderings. This is a rendering of a view from the basement. It's in a photograph. We took about 30,000 photographs and a whole bunch of laser scans. We localized those photographs, generated a 3D environment, and you're looking at a rendering from that 3D picture. It looks like a photo. I could have probably told you this is a photo of the place and you would have probably believed me. The reason why it's so great is because we were able to embed all of the detail in there into the 3D environment. So now this admittedly takes a long time to render in your typical computer. But if you have some of the latest GPUs that use things like, deep learning technologies to do rendering and so on, this can be rendered in real time in a kind of maybe a beefy computer, let's say. And here are some more visuals from the same environment. So this is, again, the basement, just extreme detail. In the first floor, right where you enter LIDS, there's a little radar up there. You can kind of see that. And again, kind of views from the first floor. Another view from the first floor. And here's a little video. So this is not a video from the environment, but it's a rendering of the environment itself. And so now what we're doing is, we're using these environments in the virtual reality system that I've kind of shown. And we're trying to learn kind of how to fly fast and do some of the interesting maneuvers in this environment. And we're then trying to just transfer that to the real environment, to the real data center, without doing any kind of modification whatsoever. And there's a lot of exciting developments on creating these kinds of environments that I can see that in the future we can create like entire cities or, entire, hundreds of buildings into sort of like virtual reality environments that then we can use, for example, in learning capacity. And so I will not talk much about the transfer just yet, but I'll talk about some of the other things that we're sort of like doing more on the hardware side to enable everything, and then I'll try to put it together in a few videos. So now that's all the learning environments and things like that we're using. We also realized that, in order to really push the boundaries, we can't just buy like off-the-shelf components, because you buy an off-the-shelf camera and it's made for your eyes, and your eyes can capture images at 30 to 50, maybe 60 frames a second. So that's what the camera is for. And then they design the computers for that speed. And then they design the algorithms for those computers. And so we've realized that we just really need to, push aside everything that's off the shelf and start again with a camera that can capture at a very fast rate on this very drone that's completely custom built and 3D printed. You're looking at a camera that can capture at 400 frames a second, 10 times more faster than what your eyes can see. Then the computers are designed for that specific task. In particular, we have some GPUs that we can fly, but at the same time, we have an FPGA on board in this computer that I'll show you a little bit more, that we can bake our own circuitry, meaning that we can sort of design the chips from the ground up and bake it in there. And then finally, obviously, those chips implement new kinds of algorithms that are designed for this fast-paced environment. Let me give you two details. One of them is, we have our own circuit board that has a real-time computer, embeds a very accurate inertial measurement unit. We even put like a few ticks around the motors, and we have an optical encoder so that as the motor turns, we can read how fast the motor is turning, so we have very precise control over it. We have also built sort of very high-speed cameras. These are very sort of sensitive sensors that you can get as sensitive as much you can get CMOS technology. So when it's very sensitive, you can run it at a high rate and you can still see, it's not dark, so you can still see the environment. We kind of pulled it together in a stereo configuration, much like your two eyes, so you can see 3D distance. And we coupled that up with an inertial measurement unit. This generates a lot of data. Each camera runs at 4 kilohertz, 400 hertz, and the inertial measurement itself runs at several kilohertz. So we can't just put the data in a normal computer. So we actually feed that into an FPGA, where we bake our own circuitry so that we can process that data very quickly. So this is kind of a video that hopefully will stream okay. It's a short video. But what you're seeing here is a drone that sort of goes through one gate, a second gate, and a third gate, turns around, goes through a fourth gate, and completes a turn. I'll play this again. It just does this in 8 seconds. During this process, it reaches about 25 miles an hour. That would be 40 kilometers an hour in a very tight space. The space measures like about 10 meters long. So it's and it's not using any kind of external aid whatsoever. It's just kind of detecting everything as it goes. And we can also do a number of other things on autonomous control. We can even put them on fixed-wing aircraft. The aircraft themselves they can hover, but they can transition to forward flight like it's happening here. We can even kind of have them do like loops and turn around and do sort of all kinds of sort of crazy maneuvers. There's a lot to talk about how they work, like from their perception systems to decision-making to controls, and there's like a number of things. Just in the interest of time, I figured I maybe pick like one of the topics and tell you more. So one of the things that we're interested in is, for example, designing their motion. So you're going very fast and you want to decide which direction to go next. When you're going very agile with a drone, or really any other vehicle, you have a lot of sort of complicated effects that come in. For example, we have very complex aerodynamics that kind of kick in. It's very hard to model. We have very complicated battery electrochemistry. For example, if you turn very quickly at some point, the voltage in the battery drops very quickly, and you need to wait for that voltage to come back down. You can't do two very quick maneuvers back to back. This is even true for electric cars. So if you have an electric car, you accelerate very quickly, and then you kind of you need to let the car rest a little bit so you can do that again. And there's a lot on the motor electromechanics too. So but now when we use existing motion planning algorithms, if you're familiar kind of with the field, what happens is that people have to use very simple kind of models so that they can like simulate them very quickly. Ideally, in a split second, you need to run 1,000 simulations so that you can pick the best. You could certainly simulate these effects, but the kind of computational fluid dynamics and things like that you would need for it would just take a long time to run the simulations. Like we're talking minutes or even hours. So here's one of the things that we did. We first focused on, let's design a single path, and let's not worry about how much time it takes to design it. let's just design the best path. And so we have this algorithm here that actually sort of models the constraints that we would face in doing the modeling. For example, like, can we pull a certain maneuver, and is it yes or no? And that feasibility constraint is modeled using a Gaussian process. And then basically we initialize the Gaussian process pretty much randomly. We'll be building the Gaussian process as a feasibility model on different kinds of things that we can do. At each iteration of this kind of trajectory design system, we'll pick a certain kind of a point and to try to test in simple simulations, in more complicated simulations, or even in real flight to see whether that was feasible or not. So now simple simulations, you can run like millions of them in a minute. The more complex simulations, you can run 1,000 of them in a minute. A real experiment, you can only do one experiment in a single minute. And so you have to decide, somehow the algorithm decides which one of these to do in a way that it can quickly make progress. And the algorithms in some way decides that on its own and learns that feasibility boundary using a very complex Gaussian instrument. So we can then design trajectories that actually beat the best human pilots. But it's a single trajectory. We basically say, go to this waypoint, that waypoint, and come back. And it takes about 2 months to design this trajectory. And it's a lot better than anybody can do. How can we do that so that similar technology now based on all these complicated simulations and real experiments can be designed very quickly? Well, we started doing kind of the sequence-to-sequence models that you may have heard about in the natural language processing world. So people have been using what's called attention mechanism, sequence-to-sequence models to do very quick translation of language, for example, or a number of other things. Maybe you've heard of like this thing called GPT-3 that can like just generate text. There was a Google researcher who thought that a system like that is conscious and sentient or something. So they're very impressive. We take the same thing. And we basically use what we did in the previous slide, and we generate that as data sets to train a sequence-to-sequence model. And the sequence-to-sequence model then learns on its own how to kind of exploit the very complicated dynamics of the system that is embedded in the complex simulations in the real flights. We start out with just imitating a simple simulation. So this is just simple simulations that you can run very quickly. We train the sequence-to-sequence model. The model quickly learns. I mean, it's not quite as good as just running the simulation, but it's almost there. And then in the second epoch, what we do is in the second set of epochs, what we do is we take a very small subset of the very complex simulation. Just like here we have tens of thousands. Here we have 200 simulations, and we just kind of overfit to that data. So you can see within that data, our accuracy improves much higher than what you can achieve with simple simulations. But then overall accuracy goes down because we're overfitting to that small data set. And then we run 2 months of reinforcement learning epochs that basically generalizes this learning to the entire data set. So you can see that not only we're doing in the data set, like start to do better and better in the data set that we've started with, but also for the entire validation set, we start to do better very quickly. With this, we can be about 6% faster than what's considered the baseline that has to use simple simulations. And this is about like humans, different kinds of experts lie within this spectrum somehow. So if you get to about 6% improvement, like they can't do more than that. And 6% sounds like little, but it actually is, when you look at the experiments, it looks a lot faster. And frankly, it could be just that little difference between saving somebody's life or not in a traffic accident. So I can show you some of the things that we can do using these types of things. So this is now not using the previous algorithm, but just kind of using some of the trajectory planning plus like control methods that we use. So it was a fast video. I don't know how well it's streamed, but I'll kind of run it once more. The drone kind of goes through, again, 3 gates, this time reaches 30 miles an hour, goes through the last gate, and even flips through the final gate to complete the turn. Even faster videos, which will probably not stream that great, but here what you're seeing is like an onboard view of the same thing. You can see like it's actually barely fitting through these constraints and turning through the gates, and really it's pretty clear that it's optimizing this trajectory overall. So I'll maybe just say that, I said that there was a flip in there. So when you look at the flip, it looks very quick. But imagine that like we can actually design these kinds of environments as systems so that their cameras run at 400 frames a second. That's about 10 times faster than your eyes. So here is a video of the same flip that's in 10 times slow motion. So basically this kind of technology, you see a quick flip and you as a human say, wow, that was very fast. But to the vehicle itself, it's actually not that fast. Things are happening pretty slowly at 400 frames a second. It has a lot of time to think through and establish the turn and obey all the constraints. So ultimately, in one shot, this is the kind of technology that we're attempting to develop. I was able to just tell you some of the trajectory generation reinforcement learning network that we're doing, but there's a lot of others that go into perception, controls, and many other areas. If you're excited about it, please go to ira.mit.edu and you'll learn more over there. I have a bit more time, so I'm going to sort of switch gears and talk about another related area where we're trying to develop sort of the very small autonomous vehicles. If you're interested in that, go to our website, lean.mit.edu. This actually is joint work with Professor Vivienne Zeh, who is in the Electrical Engineering and Computer Science Department here at MIT. She's a member of the Research Laboratory for Electronics. It's a big laboratory, just like Lids, just kind of right across from Lids. And so we have a really kind of interesting collaboration that I really like. We actually have a small research group that we completely co-advise. The group itself works not only in autonomous vehicles, but also in computer architecture and integrated circuits. And I'll tell you more about it in a second. So, when people think about consumer drones, like they think about drones like this, and, I've kind of shown you drones like this like about this size in the previous set of slides, but this is not the smallest drones that we can build. We can build, rotary wing drones as small as this that can fit in your palm. And we can even build drones smaller than this. We can build things that can fit on your fingernail. So now at this scale, it turns out it's not most efficient to kind of have motors, but it's more efficient if you flap your wings. And so, it's a flapping wing drone that can do the same. So now, this could have very exciting applications. Even the previous one, imagine you would have a little drone, you put it on your palm, you lift it up a little bit, it flies up, and then it starts filming you indoors, and you can do a little dance and put that on TikTok, for example. I imagine these kinds of drones would actually excite a lot of consumers. If they existed, they could be quite useful and in numerous ways. They don't exist. They don't exist, I don't think because there's no market for them, but I think they don't exist because we just cannot put computers in them to make them autonomous, make them useful in some way. And so this is the kind of thing that we focus on here. How can we actually fit the computers in these devices so that they can be fully autonomous? And it doesn't end here, actually. In aerospace applications, you can even imagine like satellites that are very small. Obviously, they can be very useful in like the low Earth orbit, and they can go around and do a lot of inspection and things like that. But, they can be useful in many other ways. Like imagine exploration. Suppose you want to explore another star. It will be very difficult to take to another star a big satellite. Like even something this big, it just has a lot of mass. It would be very difficult to propel it and take it to another star within a century. If you really want to get to another star, you have to build things very, very small. Things like half the size of a credit card, maybe even a lot smaller, actually. And so how can you put computers in there so that they can be autonomous when they reach their destination? They can make the right kind of decisions, get the right kind of imagery, analyze it, and send it back here. Applications are many. I just, kind of talked about aerospace, but you can imagine like there's robots like water gliders, soft robots, or printable robots. There's a whole cohort of things, all of which expand about 1 watt of energy, maybe even a lot less. Like flapping wing drones, for example, they need 100 milliwatts to like lift themselves off the ground. Now, all the existing computers that we have are about 10 watts. Some of them are 100 watts so that they can run autonomy algorithms. The kinds of things that we deploy on self-driving cars are kilowatts. So imagine 100 milliwatts to lift yourself, and then 10 times or 100 times that, or maybe 1,000 times that, so that you can turn on and off some transistors so that you can see what's happening around you. That clearly won't scale. Somehow we need to find a way so that the computers can spend something like 100 milliwatts or 1 watt at most so that they can be fully autonomous. So basically we do that by designing chips from the ground up. So we don't use existing computers. We design new computers. Alongside, we have to design new algorithms so that they're extremely efficient in what they do. This is not very new, actually. This is where the consumer device industry is also going. So today, if you buy a phone, there's a lot of circuitry in the phone's main chip that actually enables it to do various different tasks without expending all your battery somehow. So in some way, it's similar, but it's different in the sense that we focus mainly on the autonomy tasks. One of the things that we've done is, we've developed a tiny chip. It's shown in here next to a little quarter US dollar. And next to a kind of a commercial off-the-shelf small drone that could fit on your palm, very small. And the chip itself measures by 4 millimeters by 5 millimeters. It has a number of different components embedded inside. It focuses on a simple task, but that's very important for robotics. It takes in a camera image. It detects little features in this camera image and tracks those features. It then integrates the tracks with an inertial measurement unit in order so that it can find out where the location of the device is. On the plot right next to it, you're seeing two lines. On green, you're seeing the ground truth position, and in blue, you're seeing the position that we estimated. And as you can see, they're very close. Obviously, it'll drift over time, but it really, the estimation is just extremely close to the real position itself. This is solving the problem of finding the location of the robot, which is one of the most important problems in robotics itself. But also you can imagine you can take the same chip and put it in your next generation augmented reality glasses so that you can know where you're looking at, so that you can render things in the right way into your glasses. So it's useful for those applications as well. Just a little bit more detail. The chip itself was designed by us, fabricated on the 65 nanometer CMOS technology at the TSMC, Taiwan Semiconductor Manufacturing Company. It runs on 1 volt supply, and it expands about 24 milliwatts in order to run between 28 to 171 frames a second camera images. It uses very little memory. When you're designing computers from the ground up, it turns out that you can do a lot of computations, actually. You can run lots of compute. That's not the most expensive part. The most expensive part is moving data around. If you try to move data around too much, that takes up a lot of effort. And so basically, we're trying to minimize data movement. We're trying to minimize utilization of memory. There's very little on-chip memory on this device. And somehow, just with that little memory, we're able to sort of make this work. The memory that's available doesn't even fit an entire camera frame. And so we need to process the camera images as they come in somehow. And so those are some of the challenges that requires us to redesign a lot of the algorithms. Frankly, some of the most important things are on sparse matrix operations. And so it turns out that you need to do some optimization that requires a Cholesky factorization, and we need to somehow find a way to implement from the ground up a Cholesky factorization chip. That's kind of what it's doing at the end. And that kind of is embedded here in various ways as the linear solver. So there's a lot of other different things. So I talked about how do we localize, how do we know where we are. One of the other technologies that we worked on quite a bit has been how do we actually look at camera images and then estimate where objects are so that we don't collide with them. So take a camera image and estimate depth. Another thing we've looked quite a bit is kind of how do we find where there's most information in a map so that we can run an exploration very efficiently. But there's even very exciting problems just in the decision-making domain. Like, for example, usually you plan a path to minimize the energy that it takes, the actuation energy that it takes to actually implement that path, meaning that you want to minimize the electrical energy that your propellers will take so that you can, go and implement it. But then in this setting, the compute energy and the actuation energies are about similar. So if you were to spend a lot of time thinking about the best possible, the minimal energy path, well, that's a little stupid because you just spend a lot of computing energy to find the minimum actuation energy path. But now there's a lot of computing energy we expended. So somehow you need to minimize the overall energy. And in some cases, the best way to put it is that you shouldn't be thinking too hard. You just kind of find some simple solutions, and maybe that doesn't minimize actuation energy, but it gets away with minimal computing energy. So there's very exciting problems across the domain that, we're very interested in and working with. And if you're excited about it, go and take a look at lean.mit.edu and you can learn more. So I'll conclude with the slide. Thanks a lot for being a part of it. I tried to leave some time for questions, if any. That wasn't too easy. And I know that it was a bit of a kind of an overview. There's a lot of other papers and publications on the websites that if you're interested, please go and take a look. Thank you so much for your attention.
Thank you.
Thank you so much for this inspiring presentation. There was a lot to digest, actually, and to comment upon. I'm sure there will be a lot of interesting questions and comments. Nihat Hocam, maybe you would like to start.
I have a technical question and an educational question, but before that, I see our president, Meryem Sondan Durkanoğlu Faiz, who's in this pose, but who has listened to the colloquium from the very beginning. She's also a close friend of Sertaç. Our president, will you be, and she's a sponsor and the reason for all these colloquia. So I thank her once more. And President Durkanoğlu Faiz, would you like to make a comment or should we continue?
Okay, Nihat Hocam, thank you. Sertaç, it was very nice to see you on the screen. I had an operation back on my back, so I am lying down. That's why I didn't turn my screen on. It was very inspiring talk, and actually I had a question, but right after you answered it, so currently I have no questions, but it was very inspiring talk, and thank you for being part of this colloquium series.
Thank you so much, Hocam. Thank you so much. Thanks a lot for having me. It was a real pleasure.
Always,
to be here.
Thank you.
And I really look forward to seeing all of you in person at some point. It's been a long time.
Visit us at Kadir Has University. We have new address, as you know.
I look forward to doing that, hopefully next summer.
Please do so, okay?
Thank you so much.
We have a participant who's raising their hand.
Can I say something first?
Please.
So on Sondan, our president's comment, I should also point that we go to MIT quite often. Actually, Sondan will just spend 2 years there. I go quite often. Every time we go there with students, no matter what, you see how busy Sertaç is, but he's always there greeting us and helping us through 20 years. Thank you very much.
It's always a pleasure. I also really appreciate, whoever the people who greeted me when I came to MIT for a week. Fevzi, for example, I don't know. I guess they're back in Istanbul Technical University, but there were a few others.
Fevzi is in Sabancı, actually. I took him there.
Okay, that's great.
So I have a quick question, 2 quick questions. One of them is research and a little science fiction afterwards. You probably have chemical sensors in these drones. And the next question is, if you have chemical sensors, can a robot go and find a place to thermocouple and charge itself, the drone? And then you have a completely forever sustainable robot independent of us. So you may want to comment on that. And second is, this is very important for us as educators, at any given time, how many undergraduate students do you have doing research in your lab? The second question I'm going to repeat in Turkish also, or you can give the answer both in Turkish. Herhangi bir anda kaç tane lisans öğrencisi laboratuvarınızda çalışıyor? Both questions, here you go.
Okay, so the chemical sensors, we haven't done much, to be honest, but I've read a lot that people will put all kinds of sensors, for example, to find like a chemical leak. It actually turns out to be quite an exciting, like a computing problem, because it's not that the chemical leak is like a little beacon, somewhere, but you need to explore the environment to see how the concentration is changing so that you can actually localize it. It turns out to be quite an exciting problem. I haven't worked on it, but I know that there's a lot of exciting research in that direction. The battery changing system, you're right. I've seen a few people work on that too. We right now change batteries by hand, in a research laboratory. We've kind of optimized it ourselves a little bit. But I've seen like some of these battery changing mechanisms, I'll be very honest, they're more complicated than the drone. like the drone kind of lands and they have some ways to like change batteries. And it seems like an exciting research area. I don't know. The battery life is kind of short, and it's not going to get better, a lot better very quickly. So I'm not sure how that kind of piece will play out. I guess we'll see.
No. Well, what I meant is that the drone sees two different chemical environments close to each other, sends two wires and charges itself, makes that decision.
Yeah, it could have been quite nice. That I have not seen, but that's a good idea. I wonder how much energy you can pull out from that system. Keep in mind, these drones are quite energy hungry. Like, for example, the hover, we might expand like 100 watts on some of these things, but maybe for some of the very small drones, it could be quite exciting that I haven't seen. Maybe I'll take that to my students. We'll write a paper about it. It's exciting. Okay, so undergrad students. I have a lot of undergrad students. Typically, I can't count how many. Admittedly, the last couple of years have been a bit of a low period because of the pandemic. MIT had certain rules on how we can engage with undergraduate students. I still had maybe up to 10 during the pandemic times, but we could only kind of give them virtual tasks. I think most of the students, a lot of my graduate students are very theoretically oriented, and so they come to my group because they're mathematicians and things like that. A lot of the undergraduates, they come because they love the lab. And so when the lab was gone, it was a little bit difficult. Just this semester, we're kind of rebuilding that. Right now, I have about 8 undergraduate students. It's normally low. It's about half the number that I support. So I'm hoping that it's going to be closer to something like 50.
So at any one time in Leeds, how many students undergraduates are there, roughly?
So at Leeds, it's a lot bigger. So, like, for example, in 2018, pre-pandemic, I've seen something like 150. Like that'll be about that size. So we have about, that many graduate students. So kind of like a bit, usually we see like a one-to-one match. But it's very different among the groups. So some groups support a lot of undergrads, some groups have none, but somehow it balances out. And so we'll typically have over 100. I admittedly don't have the number off the top of my head, but we engage with undergraduates quite a bit. 100 is a lot at MIT because, we have about 1,000 undergraduate students for every class for 4 years. And so, we have 4,000 undergraduate students. We see that easily like 85% of them do some form of research lab involvement. So it's almost everybody.
Thank you for the answer. Sondan Hocam is raising her hand.
Sertaç Hocam, I have a question. The algorithm you develop for larger drones moving in larger space can be used in a bloodstream. Imagine you have really small drones and moving in the bloodstream. The similar kind of algorithm, can they be used in those small environments?
I would think so. Admittedly, we still, I think that some of the technology that is being developed for autonomy is still very new, I would say. So I don't want to kind of, I think it's maybe important not to overhype it. I would think so, but, we still need these bulky computers. It's easy to be slow, but, going at operate like slow, meaning it's so slow that you feel like you could just kind of operate it yourself and it'll be fine, like it'll be faster. I think we're still having a bit of a hard time like going at operational speeds. But I would imagine, yes, I think eventually, I don't see why not, like we couldn't build drones that's like about this size, and they could be at operational speeds, like they could go as fast as somebody can run. And then they could go into all small openings and do different sets of things. But the way I see it is that in order for us to get there, I think we're going to have to build new computers. And so this is potentially definitely a multi-year. I don't know if it's a multi-decade effort, but certainly a multi-year effort to get to that kind of an application, I think.
Okay, thank you, Sertaç Hocam.
Thank you, Sondan Hocam. We have another guest raising their hand. I can't see the full name. Panay. Could you turn your mic on, please?
It may be Erdal Hoca. Erdal Panay.
Erdal Hocam. Erdal Hocam, mikrofonunuzu açabilir misiniz?
İyi Panay. İyi Panay.
Şimdi açtı sanıyorum hocam.
Okay. Can you hear me?
Yeah, it is Erdal hocam.
Can you hear me?
Yes, Erdal
Yes,
hocam.
yes,
We can hear you.
Okay. Thank you so much. Sertaç hocam, iyi günler. It is very interesting to listen to your presentation. It's really inspiring. At the same time, I'm very glad to listen to you because you are originated from the Istanbul Technical University. I heard that. I'm not sure which department because I am also originated from the Istanbul Technical University from Faculty of Electrical Engineering. Are you?
Yeah, so I did mechanical engineering.
Oh, you are doing mechanical engineering. Okay.
But I also did like a double degree in computer engineering.
In computer engineering. Okay.
So I kind of have been in
I was,
which was not a good idea, but it worked out okay.
Okay.
I tried to finish both of them in 4 years, and it did finish, but
good.
Yeah. Anyways, I would recommend a double degree to students here if people are interested, but I wouldn't recommend trying to finish it very quickly. I think it's good to kind of like give it some time to take it in.
Yeah. Well, okay. I am in electrical engineering, as I said, and basically I'm working in the communication field. It's very interesting. You know, I resemble the drones moving actually to a new generation low orbit satellites. Maybe you heard of this one, for example.
Yeah, we're very
especially the recent
about
one, you know, they are throwing hundred thousands. The purpose is to improve the internet communication between the, you know, the peoples.
Yeah.
Right. And then those low orbit satellites are moving in a so fast velocities, actually, that yet they're able to communicate to each other. At the same time, they're communicating the base station on the Earth here. So I was wondering, actually, you haven't mentioned, is there any possibility that the drones can communicate to each other, for example, to organize, not to collide to each other, for example, if they could have some kind of communication, because you didn't mention anything about that.
Yeah, I didn't get into that, but it's actually like an exciting research area that we're now a little bit involved in. We're trying to build kind of systems that can become a part of what's called, like you call it, sort of small sats. They cost about $100,000 to kind of put up.
Right.
Orbit. We're actually trying to prepare one to go onto low Earth orbit. We're also trying to engineer another one that'll go to the
You mean satellite, you said?
Yeah, like a small satellite.
I see. Okay.
So we're working with a group here that, you know, kind of, it will have sort of like ion thruster system so that it can turn itself around. We'll have a certain kind of a camera to look at Earth observation. We're even trying to engineer a version of it so that we can send it to the International Space Station. It seems like there's a lot of rules on kind of doing that, but we're trying to get through it. I'm personally very excited about the space applications.
Right.
I think communications is one of them, but there's like just so much more that can be done in space. Like manufacturing in space is something we're very excited about.
But I'm particularly interested to ask you, I mean, not the satellite, but drones, actually, you know, as you described that lots of drones is moving at the same time, for example, in a coordinated way, for example. Is it possible that they can communicate to each other, or how can control to each other, for example, in order to not collide?
Yeah, I guess I'm using the word satellite more broadly to be like anything up in orbit. But, you know, yes, of course, like we can call them drones if that's more meaningful. Yes, they can communicate. So like, for example, we have laser communication equipment on board. So, you know, it beams a laser to another drone, let's say, or another satellite. And the other satellite receives the laser beam. It turns out you can pulse the laser beam or, you know, put information in certain other ways that is kind of similar to a fiber optic cable. You can actually communicate a lot better in space than you can communicate down here on Earth, because there's really nothing in between. It's literally nothing. Here you have air and things like that get in the way. Up in space, it's, you know, surprisingly, it's a little easier.
Okay, thank you so much, Sertaç.
Thank you.
Thank you so much for the question and the answer. Nihat Hocam.
Yes, listening to Erdal Hocam, whose interests I know, another opening may be, are there underwater drones? Since it's so hard to send signals inside the underwater, as Erdal Hocam and people
Yeah, that's an interesting one also. Yes, you're right.
To have drones that function underwater without having to communicate with the surface could be interesting. Are there efforts in that direction?
Yeah, I think that, one of the exciting things about autonomy is when you don't have access to, for example, things like GPS, which is one of the other limitations of being underwater. And so you don't actually know where you are. Like, for example, for these submarines and things like that, like they kind of go underwater at one point and then they cross the ocean and go above water. And even for them, they're human driven, but how do they know where they are? And so autonomy really helps in that regard. So ideally, like when you don't have any sensors, you don't have any communication, how can you be fully autonomous is the kind of problems that we exactly focus on. And so, or when I say we, not just my group, but sort of like broadly as a community nowadays. I don't do underwater robotics myself, but from a lot of the colleagues, I know that they work on similar problems where, you, for example, need to look at a visual imagery underwater, you track the environment, and then you kind of try to track how far you've traveled. Maybe you try to localize yourself on a landmark that you've seen before. Things like that are kind of extremely important, I think, to people. So maybe that was a non-answer, but I think a short answer will be we're not working on that so much, but just kind of looking at the literature, I can see that the problems are a little bit similar in some ways. And the fact that you can't communicate and you also don't have GPS requires more and more autonomy on top. You can still do near field communications. People have done things like ultrasonic that doesn't carry too much data, but again, you can use light. And so if something is nearby, you can basically shine a light. And if you can do that very well, it's as if you have like a fiber optic cable connected. So now something like underwater, you can't do that at long distances because water just dissipates the light. In space, you can do it at very, very long distances, to the point where you just need to, be careful with like gravitational effects and things like that. But otherwise, light will keep going.
Right.
Thank you so much. We have a question from Dilek Tükel Hocam from the chat. She's asking, do you have any work on biological robotics and which innovative materials may be used in future for miniature robots?
I do not. I've seen a lot of work on like biologically inspired robotics. And so, people will build synthetic like things, like, for example, flapping wing vehicles. They're inspired from biological organisms. And I know that people are now more and more excited to just like build biological systems. Like, you can take a little insect and somehow put a chip on top and, control it. I've seen those kinds of things, but admittedly, we don't have much work there. And I'm not too much up to date on how people do those kinds of things.
Thank you.
Thank you. I appreciate the questions. I'm very excited.
Are there any questions or anyone who would like to contribute and make a comment, maybe? I can't see any hands raised. Nihat Hocam?
I'm not monopolizing since there is some space for me. In biological interactions, you don't have to stay the same size. You can have underwater robots or above air robots that interact semi-domestic creatures, such as dolphins, which can be trained.
Yeah,
and dolphins can be basically, it could be like a shepherd dog or something, guiding dolphins in underwater using a robot.
Yeah, one of the exciting things that I actually, read about nowadays is our people are trying to sort of like communicate with whales. It seems like they have a language, but we just don't know how to decipher it. And some of the advances in like these language translation models and things like that are helping decipher what that language is. And so I don't know, one day I could imagine that maybe there's a way to communicate with them, and there's some robots plus like these animals essentially working together in a variety of tasks, maybe.
One more question. So
Please.
last question, promise. So now, since you use virtual reality after taking 30,000 photos so well, you don't need a building, you don't need a laboratory, right? You can do this from your home.
Yeah, I mean, I guess
the president of MIT hear this, but you can work without a building.
That's actually an interesting kind of a question, kind of thinking about, where we're going. But I mean, maybe one day we really create like these virtual environments. There's certainly advantages. Like, for example, once I have a virtual lab, well, I can make 1 million copies, and I can run 1 million experiments that I probably couldn't have done it here in the physical space. We're still at the place where, we're using the physical space quite extensively. So I wonder if we're ever going to see that go away. But admittedly, these virtual environments have been quite valuable in a way that's synergistic with the real environment for now. And maybe one day everybody will be virtual. I don't know.
Very good.
But at least not yet.
Thank you so much, everyone, for your questions and comments.
Thank you.
And
we enjoy talking.
Thank you.
Yes, we very much enjoyed it. And
really?
Actually looking forward to meeting you in person, hopefully, in Istanbul, and
Right.
hosting
Likewise.
Kadiras as well.
Likewise, I really hope so. I hope we'll make that happen. Thank you so much for having me.
Thank you very much, Sertaç. And we'll be in touch. Thank you very much.
Thank you. Bye-bye. Thanks, everyone.
Bye-bye.
Thank you, everyone. We'll be meeting in 2 weeks, hopefully this time with a face-to-face meeting at Kadiras campus. But our online colloquia will also continue throughout the academic year. Thank you so much. Goodbye.
Bye-bye.